Okay, so let's get started. We're going to start with Unit 4. It is the probability unit, all right, and it definitely has some tricky components to it. So please reach out, ask for some help. Come see me in my office hours, go see the tutors, do something. Okay, so excuse me, a little burp there. All right, well, let's get started. Okay. Probability is the way that we can express the chance of an event occurring, okay? And there are three basic types of probability. There's experimental probability, which is when predictions are made based on past data collected, like tossing a coin, or it's what the basis of weather forecasting is, horse racing, things like that. There's subjective probability. That's predictions that are made based on educated guesses. That I guess would also be like horse racing or sports betting in general. And then there's theoretical, and theoretical is where the predictions are made based on the experiments with equally likely outcomes. And that's what we're going to be doing, okay? So the key here is it's equally likely outcomes, all right? So theoretical probability can be described as a situation with equally likely outcomes that M of those N outcomes correspond with a particular event. I know that is just a whole lot of word gobbledygook. We're going to just do a bunch of examples and you'll understand. So basically, the probability can be found by P of an event is equal to M divided by N. And this P stands for probability. That is a capital P. This is similar to the notation of f of x, but this is the probability of, and then whatever the event is. We roll a 5 on our die. We draw an ace in the card, something like that. This is how we are going to compute that. The result of any experiment is called an outcome, and an event is any particular outcome or groups of outcomes. Okay, maybe we want to pull a red ball and a green ball out of something. That would be an event. But it is a compound event, more than one thing. A simple event is an event that can't be broken down any further. So it's just like rolling a 2 on a dice would be a simple event, but rolling an odd number on a dice would be more of a complex event. And the sample space is the set of all the possible outcomes. So let's see what this means. So basic probability, given that all outcomes are equally likely. This is why you can't apply this to everything that you can apply probability to, and that this is just a very small little subset of probability that we're talking about. Just enough to give you a little bit of information, okay? So we can compute the probability of an event E by using this formula. P of event E is equal to the number of outcomes corresponding to event E over the total number of equally likely outcomes. This is not a subtraction. This is equally likely outcomes, okay? So first I ask us to find the sample space of a 1 6-sided die. And remember that a dice, 1 6-sided dice, that's one thing. And we want to know what are the different things that we could get from one-sided dice. Well, we can roll a 1, we could roll a 2, we could roll a 3, we could roll a 4, we could roll a 5, we could roll a 6. Could we roll a 7? No, there's not a 7. There's not a 7 on a 6-sided die. If we were rolling a 20-sided die, there would be a 7. But this is a 6-sided die. And so the only sample space, the only possible outcomes, the sample space is the possible outcomes. The only possible outcomes are those 6 digits, okay? Now, a simple event would be rolling a 1 or rolling a 5. But a compound event would be rolling a number bigger than 4 or rolling an even number or an odd number, something like that. So I'm sure that you've seen dice, but usually I teach this in a classroom and I bring dice in and we mess around with the dice a little bit. So can't do that here, but here is a nice, beautiful picture of dice. Okay. So let's look at our first example. We roll a six-sided die and calculate the following. So first thing I ask is for the sample space of the experiment. Hold on, this thing is super thick. Let me bend it up a little bit. The sample space for the experiment. So the sample space here, as I just said before, is 1, 2, 3, 4, 5, and 6. That's the sample space. Now let's look at our first probability. It wants us to find the probability of rolling a 1. Well, the way we find probability here, so the probability of the event is equal to the number of outcome of the event. Oh, I don't know. Okay, got it. Of the event over the total in the sample space. That's really what goes on the bottom is the total number in the sample space. Oops, space. Almost wrote sample space. Okay, so rolling a die, that only happens once out of the 6 numbers in our sample space. So 1 in 6 is equal to 0.166666. It continues. Okay, so this is the probability written as a decimal. And then we could turn it into some percentages when we want to answer some questions here. We could say that this would be 16.6% chance of rolling a 1. Okay, let's look at the next one. What's the probability of rolling a 5? Well, the probability of rolling a 5 is the exact same thing as the probability of rolling a 1. Right? It's the exact same thing because there's only one way to roll a 5. There's only one way to roll a 1. Now, so these two are what we would call simple, right? These are simple, just one thing. Can't break it down any further. Now, find the probability of rolling a number over 4. Now, this is where probability starts getting a little bit more difficult. You have to read critically. You really have to read it critically. So this is rolling a number over 4. So number over 4. Well, the numbers over 4 are going to be 5 and 6. So this is really asking us to find the probability of rolling a 5 or a 6. Well, that is 2 chances. There's a 5, that's 1 chance, or a 6, that's 2 chances. So 2 out of those 6 things could happen here. So 2 out of 6, that is equal to 1/3, which is equal to 0.3 continued, which if we wanted to write it as a percentage would be 33.3% chance of a number over 4. All right, cool. Let's keep on moving here. So our next example says there's a bag that has 20 cherries in it. And 16 of them are sweet cherries and 6 of them are sour cherries. And if you pick one cherry at random, what's the possibility that it is sweet? So there's our question. So we're going to write it as a probability. So we're looking for the probability of the event, and the event here is that it's sweet. Okay, that's the event. Now, we ask ourselves, how many sweet are in the bag? So there's 14 chances out of how many total are in the bag? Out of the 20. And so when we do that and I simplify this fraction down, we get this to be 0.070, which is 70% chance the cherry is sweet. Okay, and so you do this one. What's the possibility that the cherry is sour? So we're going to go P of sour and let you finish this guy out. How many sour can we get? 6 out of 20. When I simplify this down and make the bottom number a 10, which is great, then we can do the math without having to do too much difficulty. And I do want you to give me a complete sentence, or at least close to a complete sentence. So 30% chance the cherry is sour. Oops. All right, let's keep on going here. All right, here I've got a clock, okay? So next example. At some random moment, you look at your clock and note the minute you're reading. It shouldn't say minutes reading, but what the minute is when you're reading, okay? So you're sitting there, you're reading your book, you look up at the clock and you notice where the minute hand is, okay? That's what we're doing here. So what's the probability that the minutes reading is on 15? So in other words, what's the probability that it is exactly 15? Well, how many places is the 15-minute mark? We're a quarter of the hour, right? So this is at the 15-minute mark. This is at the 30-minute mark. This is at the 45-minute mark. And this is at the 0-minute mark, right? Just reminding you. So how many times do you hit 15? That can only happen once. Out of how many minutes around 60? Our sample space here is 1 through, actually 0 through 59. Or we could have said, let me just say 1 through 60. It's easier for me to say it like that. Is 1 through 60, right? 1 minute, 1 minute right here. And this would be 60 at the top, 0 or 60. Okay, so 1 and 60, if we do the math there, that is equal to 0.016 repeat. And when we write that as a percentage, that's 1.6% chance. It is exactly at 15 minutes of the hour. Okay. Now, what's the probability the minute reading is 25 minutes? Oops, sorry about that. That is the exact same situation. Oh, what just happened there? What just happened there? I'm just going to do this to make it, I don't know what's happening. Okay, so that is the exact same thing as 15, exactly 25 minutes. There's only one place on the clock where it's 25 minutes. It's not 25 minutes over here. It's only 25 minutes in one place. So that's 1 in 60. Again, that's going to give us 1.6% chance. It is exactly 25 minutes. Exactly at 25 minutes. Okay. Now, what's the probability the minutes reading is 15 minutes or less? Okay, so now we've got something. I want to change colors. Now I'm messing it all up. Okay, well, I won't change colors. Now it is 15 or less. Now, if we look there and look at 15 or less, there are 15 ways to get 15 or less. And that is 25% chance, 15 or less. And by the same reasoning here, what's the probability of the minutes reading between 30 and 45? Well, between 30 and 45, there are 15 minutes again in between there. So the probability between 30 and 45. Thirty and 45 minutes. Okay. I don't know why this won't go away, but okay. Now, let's talk about playing cards because when you start talking about probability, one of the easiest ways to teach it has always been with playing cards. Of course, in the past couple of years that I've been teaching, I've noticed that fewer of my students really ever do anything with playing cards, don't understand playing cards, don't know all the characteristics of the playing cards. So let's spend a minute to talk about a deck. Now, a deck of playing cards, there are 4 suits. There are clubs, diamonds, hearts, and spades. Okay. Each suit has 13 cards in the following rank. There's an ace. Sometimes it's the low card, depending on the game, and sometimes it's the highest card in the game. And cards numbered between 2 and 10. So there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there are the jack, the queen, and the king. Now, all of those cards, you have all of those cards for each suit. Okay, so we have clubs, and the clubs are black in color. The diamonds are red in color. The hearts are red in color, and the spades are black in color. I'm going to even write what they're called here because I can't assume. Now I have a picture. Oh, so there's 52 cards in the deck, usually plus 2 jokers. We will not be counting the jokers. If we count the jokers, there's 54 cards, and we're not doing that. We're just going to deal with this. And so let me show you. Here's what a deck looks like. As you can see, here are our clubs, ace, all the way through king, spades, hearts, and diamonds. All right. And it's to be noted, and it's not really noticeable on this particular deck, but it is to be noted that usually all of the royalty, all of the face cards, that's what we call these here, the Jack, Queen, and King face cards because of the cards with faces on them. We call these guys, well, no. Blech. The interesting thing is usually in a deck of cards, the club king looks different than the spade king and so forth. So that's not the case in this particular set. They all look the same, just inverted. And there's one sneaky joker stuck in this guy. I didn't notice that, but there is one sneaky joker in here. We're not going to be dealing with jokers, but there are 2 jokers usually on a deck, but it's not included in the 52 cards. Okay. Now, I might scroll back up here for us to look at a couple of things, but mostly I'm going to depend on you to do a little bit of learning on a deck of cards. And if you don't have a deck of cards, if we were in class, live class, I'd have cards in class, okay? But anyway, all right, so Example 4, compute the probability of randomly drawing one card from and I'm going to put in a qualifier here, a 52 card standard deck. Okay. All right. So that means that the sample space is all 52 cards. So that is the number in the denominator. All right. So what is the probability? So we've got the stack of cards. They've been shuffled, fanned out, and you're going to pull one card out of there. What is the probability that you'll get an ace? Well, remember, it's the number of possible outcomes. So there are 4 aces over the total outcomes, 52 cards in the deck. So 4 divided by 52 is 0.08. And so we get 8% chance of an ace. Okay. And just like I showed you earlier with the dice, there are 4 aces in a deck. There's also 4 sevens in a deck. So let's look right here, right? Here's our 4 aces. Here's 7. There's 4 sevens. So, yep, that makes sense here. So this is going to also be the same. All right, now how about a heart? Well, that's different. Let's look up here again. Hearts. There are 13, plus this joker that doesn't count. There are 13 hearts. So my chances of pulling a heart is going to be 13 out of the 52 total cards. And that's going to give us 0.25, which is a 25% chance of a heart. And like that makes sense, right? Because if there's 4 suits that have the exact same cards, then if we're just talking about pulling one of those suits, then that's a quarter of all the cards. So that actually makes sense. And then finally, pulling a face card. So remember that we have a jack, a queen, and a king for each suit. So times our hearts, our clubs, our spades, and our diamonds. So there's a total of 12. So this is going to be 12 over 52. And that is 0.23, which is a 23% chance of a face card. Okay, awesome. Okay, well, here's some facts about probability. Probability is never, ever, ever, never a negative number. Ever, 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 never, ever, ever, ever. Okay? It's never a negative number. If you do the calculations, you get a negative number, you screwed up somewhere. All right? An event is called impossible when the probability is 0. An event is called certain when the probability is 1. These are very, very rare to get zeros and ones, okay? And the probability of an event is always going to be between 0 and 1. It is never going to be bigger than 1. Never. Larger than 1. Ever. Okay. Sometimes you might hear people using some things like, I've got 1,000% chance of doing something. That is really not real probability. That's people just using that language and not really understanding what probability is. Probability is only going to be between 0 and 100%. Okay. Now, we're going to start talking about something that's really, really important. It's a it seems like a really little detail, but it is going to snowball into a very big issue. Okay, so let's be sure that we understand the difference between the mathematical and the mathematical or. So we're going to start off here for and here we're dealing with independent events. And so first I need to make sure you understand what an independent event is. An independent event is when the sample space is exactly the same for multiple events. And I'm going to give you a for instance, it's like replacing the cards when you're drawing. All right. So when you're drawing cards, say I've got a bunch of cards and you're drawing one card out. Is it an ace? Is it not an ace? And you draw a second card out, your probability, if you do not put the original card back in to make it independent again, your probability is now dependent on that first card that got pulled out, and now it's dependent. So when I say independent events, I mean that they're equally likely no matter what, that nothing has changed from the first draw to the second draw, which means whatever you drew out the first time, you have to replace to make the second draw. So it's not from a different pool, if that makes sense. So, um, hopefully, hopefully that makes sense. Okay, so if events A and B are independent, then the probability of both A and B occurring is the probability of A and B is the probability of A times the probability of B. All right, and that seems really, really simple, but a lot of times in math, we just say things that are really, really stupid simple. I want to see if I can't hide this stupid. There it is. Okay. I feel better now. All right, let's change colors because I am tired of that blue. All right, here we go. Here is our next example. You have a deck of 52 cards. You draw one card, then replace the card and draw a second card. Now that means that it's independent. Okay, and because it's independent, P of A and B is equal to the probability of A times the probability of B. And that's what we're going to do here. So the probability of getting two aces, that's going to be the probability of getting one ace, 4 out of 52. We just did that. And then putting that ace back in there. And then what is the probability again? It is again 4 out of 52. It is the exact same probability because we're looking for the exact same card. And that is going to give us 0.006, which is equal to a 0.6% chance of two aces. Okay. Now let's look at the two hearts. So the first heart pull is going to be 13 out of 52. And then we put that heart back and we draw again. That is still 13 out of 52 cards. We put the card back. All 13 hearts are back there. All 52 cards are back there. It is independent at this point. Okay. And that's going to give us 0.0625. And that is a 6.25% chance of two hearts. Okay, now how about two face cards? Well, there are 12 face cards in a deck. And then we put it back all back and we do it exact same thing again. Now, it doesn't matter if this is jacks and queens or whatever it is, it's just face cards. And this is going to give us 0.05, which is going to be 5% chance of 2 face cards. All right. So that is for the and. Now, what about the or? Okay, so let's talk for another minute about the and or here. Let me come back here. Let me change colors. When we talk about the mathematical and, sorry, big and obnoxious there. When we talk about the mathematical and, it means this and that, right? Whatever's in this and whatever's in that. Okay, ace and queen. Uh, 7 and 5. Okay, this and that. That's just very straightforward on what it means. But when you deal with the or here, it also means A and B. So it'll also mean this and that, but not in both. Okay, and I want to just say it that way, and that'll help you kind of remember how to run this particular formula. So when we're doing for probability of A or B for independent events, then the probability of A or B is the probability of A plus, now notice, and is times, or is plus, A, probability of A plus probability B minus the probability of A and B. Okay, so A and B means it's in both, it's in the intersection, or means one or the other. Okay. And let's please remember that this is what the and is. Okay. All right, so let's do an example, shall we? All right, let's get back to the pink. Okay, you have a deck of 52 cards and draw one card. Find the probability of the following: that you draw a king or a queen. So the probability of A or B is equal to the probability of A plus the probability of B minus, and watch out what I'm going to write here because this is really helpful. This really helped me when I saw this. Probability of A times probability of B, which is just the same thing as the probability of A and B. But let's just put it all together kind of like that. All right, so let's see here. Probability that we have a king, well, there's 4 kings in one set of cards, plus the probability that we have a queen, well, there's 4 queens in one set of cards, minus, and then we multiply these two things together. 4 over 52 times 4 over 52. Okay, when you do the math there and you rock it all out, it becomes 0.148. And so that means it is 14.8% chance to get a king or queen. Okay, let's look at the next one. The probability that it is a spade or a 5. Okay. So the probability that it is a spade, remember that there are 13 cards in each suit. So there are 13 spades. Plus there are only 4 fives, one for each suit. And then we say minus, and it's the first one, 13 over 52. Times the second one, 4 over 52. This is the pattern every time. And when we do that math there, let me flip my page. anchovas. We get 0.308. So that means that there's 30.8% chance to get a spade or a 5. Okay. All right, let's have you do. Now this one's kind of a ringer. Remember that there are 0 jokers, but let's do this you do. I'm going to write the formula up here. Give you a couple more seconds. I could use some water. Okay, Mama's still sleeping. I'll get this whole thing done. Okay, hopefully you have moved forward with this. If you have not finished your you do, please pause the video now and finish it. And then let's go ahead and jump on here. So we got the probability of red or joker. Now, half of the cards are red. Hearts are red, diamonds are red. Spades and clubs are black. So for probability of red, it is going to be 26 out of 52 plus the probability of being a joker. I gave you a hint there, 0 out of 52. Minus, and then we multiply these together, 26 over 52 times 0 over 52. Well, hopefully, you know anything times 0 is 0, adding in 0. So 26 over 52 is 0.5. So we have a 50% chance of red or a joker. And then here, black or odd. Okay, so we've got 26, 52 plus. Ooh, now we need to do a little bit of work on the odd cards. Let's see. I guess we'll call the aces are odd because it's 1, 3, 5, 7, and 9. Those are the odd cards for each suit, right? 1, 2, 3, 4, 5. So we have 5 cards times 4 suits. So that's going to be 20. 20 odd cards. Okay, so we had to figure that out a little bit. And now we'll do our 26 over 52 times our 20 over 52. And let's see, by the magic of me already doing the math, but doing the math wrong because I didn't count the aces. But here I'm going to count the aces because they are kind of ones, right? So let me break out my calculator and fix the math. From my notes, I changed my mind, obviously, since I wrote my notes. I didn't put up a calculator here because the math is not the kind of math that you need some instruction on how to do it in your calculator. But if anybody's having any trouble, please don't hesitate to holler at me. I'll be more than happy to help you or put up a video tutorial or something like that. Okay, so this is going to be 69.2% chance. And I don't know why I went out that far, but I just did. Chance that card is black or odd. Okay, awesome. All right, I believe this is our last example. Yay! Now I gave you the data in kind of a weird way. I gave it to you in this weird table looking thing. I did that not necessarily to confuse you, but to kind of teach you how to pick information out of a table clearly. Now notice that we have and or, and you're going to need to use those formulas. For the and formula, it is going to be probability that A and B, how does that and go? That's the probability of A times the probability of B. And then our probability of A or B is the probability of A plus the probability of B minus the probability of A times the probability of B. Okay. All right. So let's do this real quick. I'll do a little green here. The probability of red and no tickets. So the probability of having a red car, let's see here. Here we are in red car. And this is our total. This is the denominator. This is the total number of cars, right? Okay. So how many red cars are there? 150. So we're going to have 150 over 665 times, and then no ticket. Now, how many cars got no ticket? 605 out of 665. So when we do that math there, 0.02, 0.205. So I'm going to write this up here. So 20.5% chance it is a red car and no ticket. Okay. Now it's red or a ticket. So the probability of red, we already figured that out. 150 over 665 plus probability of getting a ticket. Now let's look about tickets. 60 got a speeding ticket. So 60 over 665. And then we don't care about none of these other numbers here. Sorry, not equals. That's now a minus. Let me say minus. I don't know why I wrote this over here. Let me just pull this off so it just looks clean. Yeah. Let's say minus 150, 665 times 60, 665. And then when we crank that out, we get it to be 0.295. So we will say that 29.5% chance it is red or got a ticket. All right. Okay. So don't sleep on this homework. Get busy as soon as possible with it. This is the very basic part. We're going to add a lot more to this. So, y'all have a good day.